And I welcome our final speaker for this session. So this is Gerard Bricogne. So he studied mathematics and chemistry at the University of Nancy in France. Then he got his PhD at the University of Cambridge. And then he had several different positions in the UK, in France, and in the US. And I believe in 1996, you founded Global Phasing. Is that correct? Yeah. So since then, he is doing global phasing. So let's welcome Gerard. And the title of his talk is Some Considerations on Diffraction Data Quality, Diffraction Limits, and Refinement Approaches and Outcomes. And actually, I just he specifically wanted to change resolution limit to diffraction limit. So probably we hear a bit more about that. So please, Gerard.
Well known? Yes, okay, very good. So many thanks to the organizers for taking the risk of inviting me, because you will see I have taken some liberties with the guidelines, and the black box I will try to open is data collection rather than software. And I'll describe how some software can be used to poke into what is going on there and is of actual structural interest. So a little joke here. We're in a new year. That's a perfect square. There may be a curse attached to it because 44 squared was 1936. And that was the time that another maniac was starting agitating about needing more territory. But New Year is always a time to talk about good resolutions. Notice the S, because I will be talking about a new type of resolution, dose resolution. So this may be a hairy idea, you'll tell me. But I will also be talking about a more commonplace case where resolution is a dirty word unless it's replaced by diffraction limits, namely anisotropy. So let me start by reminding you, you won't have time to read all this, but that we use crystals as a way of enhancing the signal to noise ratio in the scattering pattern. Oh, should I set this timer? Oh, yeah, 30 minutes. Just to remind me when I'm about to expire. So it's a way of gathering the scattering patterns of individual molecules through constructive interference into Bragg peaks, and thereby summing the scattering powers of all the constituting molecules and sort of emerging from the background noise that single molecules would give, or smaller assemblies. So this makes it worth growing crystals. This is what everyone knows. But in using those crystals, we have to consider rather difficult compromises. So first of all, and here James's presentation has been terrific in covering what I'm going to sum up here. Let me put my own timing because this thing doesn't seem to be working. Sorry. So we, in any given diffraction configuration involving the beam, the crystal, the detector, we can only see a two-dimensional section of three-dimensional reciprocal space. So to fill that space, we can either rotate a unique crystal, well-known. We can take all these lots of snapshots of microcrystals in random orientations, and there are intermediates between those two extremes. But the problem is that you don't just measure an intensity the way you measure a voltage. Intensities are measured through a counting process, and that is intrinsically noisy. The variance is equal to the mean, and you cannot negotiate that. So to get accurate intensity measurements with a high value over sigma, you need not just to have no background, but you need to have lots of photons in the peaks. And to get lots of photons in the peaks, you have to put lots of photons onto the crystal. And there is only so much that a crystal will tolerate without losing its order, and we lose the signal. And when you avoid this in X-FAIR experiments, then you are back to a worst possible version of problem number one. So I've summarized this into a little reference to this Humpty Dumpty nursery rhyme. Humpty Dumpty sort of fell down from a wall, broke into pieces, and it was just impossible to put him together again. So what's the metaphor here? It's just that you can get a whole data set from a macrocrystal if the conditions are right and you do things right. But it takes lots and lots of sparse data sets to assemble measurements for all reflections from smaller crystals. And then you have to put those together again. And this is really the topic of James's talk at the beginning of this session. The problem is that you never get back to what you could have had if you had had all these pieces into a single crystal. Not just because the signal to noise ratio may not be the same, but there is variability. There is a lot of accessory parameters or fudge factors that you have to apply, especially for very sparse data sets from serial methods. And it's the estimation of these, such as partialities, for instance, in serial crystallography, that limits the accuracy of the final data. So that's the point. Developments have expanded enormously into this region of serial methods on microcrystals, microcrystallography, multi-crystal data collection. And of course, sometimes they are necessary, but you can't beat, that's the hunch, you can't beat what you would get from a bigger crystal. The trouble is that over a couple of decades of evolution of instrumentation and protocols, speed, automation have meant that even a big crystal, and here, note this remark here, what I'm talking about is a motivation to do this better that arose a good decade and a half ago. Things have improved. There are lots of efforts that can result in an improved ability to collect the best data from macrocrystals. But macrocrystals have certainly not been the focus of attention, and I will just describe something on this. I'm mentioning at the bottom here that if you want to look at data quality that will motivate you to want to do a better job, you can do this with star and ISO. But before I use star and ISO as a data visualization facility, I would like to say a few things on what it is about. It is about dealing with anisotropy in diffraction patterns. And this is, it is in this context that the word resolution, in the singular, is a dirty word, because there's just no way that you can, if the diffraction pattern of your crystal extends further in some directions than in some others, you cannot come up with a satisfactory definition of resolution and of resolution selected data to work from without a little bit of thought. And it's remarkable how long it has taken for the habit of isotropic thinking, of talking always about the resolution of a data set, and the way in which it encloses the best data in a spherical shell, how long that has taken to get through. So star and ISO server has been quite, I could spend the entire talk commenting on this picture and pointing out what you can do and shouldn't do, what you would be inclined to think, but cannot really justify. Here I will simply say that StarNISO has been a good facility for the community. By the end of this year, we should reach 30,000 successful runs. And we've had terrific feedback and appreciation on what the treatment performed by StarNISO does. For this, I will refer to you to a discussion that took place on the CCP4 bulletin board in October 2022. It started with a help request for running the PRF procedure on a data set that was strongly anisotropic. And then at the same time, there was a discussion on anisotropy in itself. So I merged those two things by creating a thread with this title that ran for a couple of weeks. And you can find that thread in these references in the CCP4 email archive. And essentially, that led to the proposal that there is a way to combine PRF and StarNISO for anisotropic data, but it is not for selecting an isotropic resolution, but instead, which in fact defines a cutoff surface by the associated sphere, but instead to adjust, to search for an optimal value for the threshold used by StarNISO to define that cutoff surface, which is anisotropic. And then you pick the corresponding diffraction limits. So that was a proposal, and very shortly afterwards, a paper was submitted that appeared after some more months. And here, I'm afraid, PowerPoint has again played tricks and lost some formatting. But there was a paper by the PRF group in Czech Republic, reporting having done exactly that on this structure, for which the PDB entry ended up being 8 BDU. They said that corrections for diffraction anisotropy using the StarNISO server with a threshold of 1.2, which is the default, dramatically improved the quality of the observed electron density maps. And no differences were observed when that threshold was lowered to 0.5. So Ian Tickle's nose in choosing 1.2 was pretty good. There are data sets for which a lower threshold would make sense, and it would be good to hear about them. But here is the picture from StarNISO of this data set. Unfortunately, gray dots on a black background don't show very well, but you can see here the outline of the final highest diffraction limit, and you can see that StarNISO excluded all the measurements in this. It also concluded that the data collection somehow missed measurements that would have been significant if they had been measured. So that's the bit for resolutions in the plural on this new year. I hope you will find this useful. The discussion in this thread covers practically everything one wants to ask and find out about StarNISO. Okay, so I go back to this slide where I was referring to StarNISO as a way of visualizing data quality in 3D. And you find pictures like this, for instance, where clearly the data have not been collected in the best possible way. Truncation by the detector edge, so the detector was too far, and then a cusp here, meaning that there is a missing contribution from a reoriented crystal because only one orientation was used. Here is a famous example. Aldose reductase was really the first macromolecular structure to be subjected to very high resolution scrutiny, including in ShellX, and to reveal this proliferation of alternative conformations that we have become used to. And yet the reference data set for this, the P1 structure, has all this missing data. It's unfortunate when you want to look at such fine structural details to not have all the data with you. This is another example. If one takes away those blue dots that indicate that there is nothing, you can see that this data set has a cusp, has a missing wedge, and yet it was meant to be used as a reference for a study with quantum mechanics and molecular mechanics. So very ambitious project, but the data could have been better. Okay, so these are the kinds of examples and earlier ones that we were looking at a long time ago when we thought we should try and develop software that could help as many beamlines as possible do proper experiments, the way in which an expert would have done them. So an expert would never have been happy with the prospect of having a cusp and would have insisted on using a multi-axis goniometer, but done calculations on the back of an envelope and kept an eye to see whether the goniometer was colliding with anything. Then the question of getting the right transmission in the beam to keep radiation damage in check would have been a preoccupation here. There are also questions of beam size, shape, and that come into play. I will leave the phasing strategies, but don't discount experimental phasing. I don't have time to show it, but it can be extraordinarily useful. So here I will give the starting point and end point of what was a very exciting development, thanks to support from Diamond to sort of join all the dots necessary to automate the use of a very heavy goniometer operating under vacuum on this beamline from Mars here. So that was extremely useful. We were funded for a period to develop the necessary software. It was not possible to test it on I-23 as such in full, but already in 2016, the IO4 team of the time was able to execute the workflow to do an interleaved 3-wavelength MAD experiment that on a crystal that had been aligned. So really full functionality here at the time, but on IO4. Then circumstances led to that collaboration having to end, but the way we had coded our workflow was such that it was possible to switch to MX³ as the beamline control system with which it was talking. And there's been a lot of work here. I'm mentioning as an endpoint today the fact that it is now completely integrated within the operations of the unattended data collection beamline that was a pioneer in the field, the Massif 1 beamline. So in a sense, that part of the development we can consider as completed, mission accomplished. We wanted to reintroduce expertise without loss of automation, where there is no loss of automation if you can be driven from outside by an unattended data collection procedure. But so this is in production now. There are several other beamlines that I don't have time to go into details of, where the workflow is connected or in the process of being finally connected. Max 4, Soleil, Alba, and so on. But I would like to give an idea of the scientific added value of having done this work, and that has been the possibility of connecting the workflow and using it on the P14 beamline at Petra, a special beamline with Gleb Burenkov as the beamline scientist, and Thomas Schneider as the head, because it has a top hat beam with a completely uniform fluence across it, a variable adjustable size, and so that however big your crystal is, we have seen much better pictures than this one, but this is a library one in a sense, that enables you to make sure that a large crystal can be fully bathed in that top hat beam during the entire experiment. And another crucial element on that beamline is that they were among the first to get a cadmium telluride Eiger 2 detector so that you can use high energy X-rays. This is all described in this paper by the Dectris group, together with many collaborators, with us among them. The big difference that cadmium telluride makes is that the detective quantum efficiency that the silicon falls very sharply at high energies remains good with cadmium telluride. So with high energies, you can get to high resolution with smaller Bragg angles, and that gives you access to things that you couldn't really hope to access with a silicon detector. So in that paper, an example is quoted based on the data set collected with our workflow by the group of Ashwin Chari, a structural enzymology group in Göttingen, who works very closely with Gleb on this and collects gigantic amounts of data. So in this case, he compared a data set collected with what was their standard way of collecting before the workflow was installed. And as you can see, with a dose of 1.5 megagray, I think, unfortunately, it's an orthorhombic structure. Very often, one of the twofold axes will be a little bit too close to the rotation axis, and you get these cusps giving incompleteness. These are the star NSO pictures produced by Autoproc. Using the workflow with exactly the same total dose budget gave something much more complete, but also gave details in the map that did not appear here and that were validated subsequently by structure analysis. So in numbers, 1.5 megagray with the standard data collection. Notice the size of the structure and the resolutions reached. This is absolutely miraculous, and it's Elam Paknia, who in Ashwin's group, who grows these miraculous crystals. No doubt about it. So that was already pretty good, but with the workflow, again, using 3 orientations to distribute the same total dose, you get better resolution. You get about twice as many observations and quite a few extra unique reflections because of the extension. Even small differences on these numbers can mean a lot of reflections, a lot more reflections. The I over sigma has increased, the multiplicity has increased. This is what leads to those extra features in the map. Okay, so dose. Going back to basics, and here Gleb had done very lovely work with Sasha Popov and published it in this paper, essentially saying you get 1 angstrom square extra B in your data for each megagray that you've put on a piece of crystal. And here with the cadmium telluride detector, he redid these experiments to establish that proportionality constant, and it really is exactly the same as they had found, I don't know, all these years ago. So essentially 1 angstrom square per megagray, whether you are looking at large doses or smaller doses. So that is crucial because when you have, as you have on Gleb's beamline and hardly anywhere else, when you have a top hat beam of adjustable size while remaining top hat, and you can bathe a large crystal in it, or a crystal in it, then the accumulated dose in the crystal will be uniformly distributed throughout the crystal. There won't be any hotspot being burnt in one place and fresh crystal outside. Everything is uniform. And that uniformly damaged or modified or radiation modified crystal, you are then uniformly illuminating with that beam. That means that the accumulation of dose, in fact, gives rise to an increase in B factor, which is common to all parts of the crystal. And this is exactly the parametrization used for scaling and for compensating decay in the scalar or aimless program. So that is key to making sure that the data you collect will be optimally scalable and correctable for radiation modification. So if you have any other instrumental setting, so if you have beams with a cross section which is not uniform, or if you put the beam through only a part of the crystal, then the contributions from the different voxels, different parts of the crystal, will decay by a different B factor because of the non-uniformity of the dose, and they will be non-uniformly illuminated because of the beam profile. So what that will produce as a net effect in the intensities you measure is that instead of having a simple Gaussian of increasing attenuation as you have in the ideal fully bathed top hat beam case, then you will have a superposition of half Gaussians of different widths. And there is no way that this can be corrected by a single Gaussian factor for each image. So a diversion here, I will go through this very quickly. When we were looking at these effects, Lee Carter and Lee Carter did the programming and Clemens helped with the display. We simulated with the radiation, the Randose 3D version available at the time, some scenarios to see how well or how badly scaling of simulated data with different illumination scenarios would behave. So this is a uniformly bathed crystal at the end of the simulation, 21 megagray. These are the attenuation surfaces predicted from Randose 3D. And this is what Aimless comes up with when it tries to scale those data. And they are pretty good and pretty good agreement. And when you look at the quotient between the two, you see that even at high resolution, at the end of the data collection, the discrepancy is only about 20%. If you now have a bigger crystal with a Gaussian beam, so that the dose will vary from 40 and some megagrays in the center down to 4 in much of the rest of the crystal, you have this problem of non-uniform damage, non-uniformly illuminated. And although the attenuation surfaces and what Aimless gets back look similar, they are really quantitatively quite distinct. And in this entire region, you have discrepancies by order at the end, an order of magnitude. Okay, so this really reinforces the unique advantage of a top hat beam going through a big crystal. And any other setting will not give you data that are as scalable as this setup will do. But now let's take a look at these data sets collected in these ideal conditions with a tool that Clemens described last year, early minus late differences. So it's a way of segmenting a data set. It's done in autoproc into an early and a late part. Just try and get a complete data set from the beginning and one back from the end. So depending on the multiplicity, of course, you can get more or less separation between the early and the late data sets. That enables you to spot radiation damage. I won't go over this example. It's in the paper that Clemens published from his talk 2 years ago. And it can really highlight radiation damage. Here in 6VZU, a classical picture, decarboxylation, a salt bridge to an arginine gets broken because of the decarboxylation here. So the arginine itself becomes disordered. So here I'm going to show you the result of this type of analysis for an ultra high resolution data set that comes from P14. One of those things that you don't really think are possible, 0.6 outcom resolution for 20 kilodalton protein at high energy, but with a total dose of only half a megagray and 11 million observations, mean I over sigma of 150 in the inner shell. It's quite phenomenal, multiplicity of 30. So the early minus late setup is shown here. Sorry. A wide separation between the early and the late data set. And let's have a look at the map. This is a region of the map at 4 RMSD. So of course, at 0.6 outcom, more atoms are resolved. If you look at the difference map after refinement in Buster that produced this map, you see that there is some unhappiness around here. Otherwise, not much. The F early minus late map at 6 RMSD has much more to say. There are pairs of green and red peaks. That means that between the beginning and the end of the experiment, in spite of the very low total dose in this experiment, some things have moved from the green to the red. So sulfur, obviously, here is getting hit and is moving because it's in a single conformation. Here, there is already a double conformation alternative modeled in, but we see that this one is getting depleted and this one is gaining electrons. And then there are pairs of peaks, green and red, that indicate movements all over the place. And if you put that map into that early minus late map into the map itself, you see that where you have those pairs of peaks, you have a kind of bloated shape that you would represent or refine by a larger B factor than other atoms. But the B factor is in fact due to collapsing by merging data that differ through small changes here. These are not, this is not because of a cell change, because otherwise all these vectors would go in the same direction. It is really something, so loss of formatting here again, it's very infuriating. So we see significant fine-grained movement of protein atoms and of waters. We see changes of occupancy in alternate conformers, and they can be tagged by dose. By this, I mean that, for instance, this alternate, if you split that one, then this alternate would go with this one, and this one would tend to go with this one. So there can be tagged by dose. There is radiation zapping. There is carboxylate going down. Whoop. Okay, right, I'm almost through. And some of these movements then get subsumed under disorder or higher B factor when refinement is done. So we are seeing this thanks to the spatial uniformity of the dose distribution through the crystal. This is what I call high dose resolution, if you forgive me for coining this expression. So it's because the dose is the same everywhere. So the degree of damage, of degree of modification in these different directions is the same in all the images. So we can distinguish outcomes that are intrinsic to the structure from others that are radiation induced or radiation modified. And of course, in ordinary data sets, you use so much larger doses on smaller crystals. And that dose is not dose resolved because typically you have non-uniform beams. All this just gets put into B factor rubbish bin. So special relevance, of course, to room temperature macromolecular crystallography, for which this is a terrific review. There is a lot to worry about there. The fact that the beams are not top hat. The crystals may not be fully bathed. Helical data collection can be used so that the mixture of radiation modification is the same in all the volumes as you go through, but that doesn't mean that within those volumes it is uniform. Okay, so this is what I wanted to present under this heading of dose resolution. There's a lot to analyze there because probably what we end up seeing as B factors, if we fine slice the dose in these ideal experimental conditions, we would probably be able to ascribe, at least in part, to these actual motions. So there is motion, just like on a cryo-EM grid. We have to do some motion correction at some stage, and we may see more than we see in the end. So new tips and old tricks. I've gone against this in a way. The tricks are the tricks that you have to improve in data collection. And the software plays the role of a method for investigating what really goes on, and that otherwise we just squash by this using huge doses of hugely non-uniform in a typical experiment. So this is what your friend Humpty Dumpty tells you. The larger the piece of high diffracting crystal you can fully bathe in the top hat beam, the better off you are. I would end by, because you say, okay, large crystals, no, be real. Who grows these nowadays and how can you get them? I would like to share a remark by Zygmunt Derevenda that very often the end point of a crystallography project is the creation of a publishable result. It's not the best possible structure you could get for that structure. But if you take some extra trouble, as he did in a number of cases, and modify the constructs to reduce surface entropy, you can gain diffraction limits improvement by, in his book, for me, let's say 2.5 to 2, it's not going to be 0.6 to 0.1, of course, but you can get better diffraction limits. And then since we are talking about size, the people who grow crystals for neutron diffraction have long been using methods that we don't use because we grow crystals at constant temperature. But there is a whole procedure of temperature cycling, which is available in these paper that I quote here. There is even hardware to go with it that make it possible to grow larger crystals if you want to. So conclusions. I think rotation MX on large crystals using special instrumentation protocols have a unique potential to go well beyond what any other technique can reach. And the parts that AI doesn't reach, it's of course determined to reach tomorrow, but in order to do this, it has to be fed with vast amounts of high quality data that are not available. And I think that these combinations of instrumental facilities and of data collection protocol will play a key role in providing them. And nowadays, we don't just have to think of our collective aim as accumulating structures in the PDB. We have to accumulate those results with the accompanying metadata in such a way that they are highly digestible by artificial intelligence. And I was mentioned the gargantuan size of this whole mechanism nowadays. Couldn't resist finding this picture of Gargantua, a sort of mythical giant in Rabelais. Right, acknowledgements. I don't have time to describe what everyone has done, but many people have been involved in enabling us to do this work. But here I want to mention the champions, Gleb, Ashwin, and Ellen, who have led us into this joint adventure. Thank you very much.
Hey, thank you, Gerard. So we're
Sorry.
really behind schedule. So maybe one question. Anybody has a question? Anybody on Slack? Oh,
there are a few questions on Slack, so maybe you can also look at them later. So I just take the latest question, which is how useful is zero dose extrapolation for correcting radiation damage?
I'm sorry, I didn't hear
Okay.
that distinctly enough.
Yeah, sorry, I have a bit of problems with my voice as well. So how useful is zero dose extrapolation for correcting radiation damage?
Well, the trouble with all these procedures for correcting radiation damage is that they are very simplistic in their thought about what dose does. Zero dose extrapolation is as if dose had a value. The point is with these crystals, perhaps bigger than the beam, or beams with a very non-uniform profile, dose has a distribution, a hugely spread distribution, so it doesn't have a value. So extrapolating something which has a changing distribution through the experiment, if you get the result, it means you are lucky, or that the experiment was done especially carefully without being asked to do so.
okay. Thank you
Thank
very
you.
much. So let's thank Gerard again and all the speakers of this session.